We are doing the unit 5, okay, and in the unit 5 we have noticed that so there is a population, and population is a whole group of individuals which is under study. So that is population, and out of population we take some sample, okay, and we study the characteristics of sample, and with the help of the sample values we try to estimate the population parameters, okay. So from the samples we want to guess about the population, and for this the estimators help us in this thing, okay. So one of the estimator we have seen is the sample mean. The sample mean is sum of the values, sample values divided by total number of values, okay. And if we find out this we have find out that the expected value of x bar that we have done yesterday, it was same as the population mean. Mu is mean of population, okay, and sigma square is variance of the population. And if we find the average of the sample mean, that was also equal to population mean. So this concluded that the x bar is unbiased estimator of mu. And second thing we have seen was uh, the variance of x bar. So variance of x bar, this was equal to sigma square by uh, root n, not root n, sigma square by n, and standard deviation of x bar was sigma upon root n. Okay, so these the things we have seen yesterday, and then I told you like when we call estimator is good estimator, how we can know. So there are some characteristics. The first characteristic was unbiasedness. Unbiasedness. So when we say an estimator is unbiased, so for that the simple rule was there. So we say T is unbiased estimator of some population parameter theta if expected value of T is equal to theta. And we have seen some examples, and in the end we observed that we were showing that the sample variance small s square is not unbiased. It is not unbiased. Actually, it is biased. So you can say that it is s square. There is biased estimator of sigma square. Okay, sample variance is biased estimate of sigma square because uh, in the end we have done it yesterday. So we noticed that if you are finding the expectation of s square, that was not equal to sigma square. In fact, it was equal to, let me see from the yesterday class. So it was equal to n minus 1 divided by n into sigma square. N minus 1 divided by n into sigma square. So this was equal to this one. So let me go back. So it is n minus 1 divided by n into sigma square. Okay. So this is the so expectation of s square is not equal to sigma square, right? So it means s square is not unbiased estimator of sigma square. So then question arise like how we can estimate the sigma square? How we can estimate the sigma square? What should be the unbiased estimator of sigma square? Okay, and to find the solution of this thing, what we have done. Uh, so for we send this extra factor on this side, so it will become n upon n minus 1 into expectation of S square is equal to sigma square. Now this n upon n minus 1 is a constant, so we can take it inside of the expectation. So you will get expectation of n upon n minus 1 into S square is equal to sigma square. So now if you see, now what is S square? So if you remember from the yesterday class, it was average of square of deviations, squares of deviations from mean and divided by total number of values. So this is average. Okay. So this is equal to sigma square. The value of S square I have put it here. Now n and n will be cancel out. So we will get E of 1 upon n minus 1 sum of xi minus x bar whole square. This is equal to sigma square. So it means this function that we have here, this is actually the unbiased estimator of uh, sigma square or population variance, we can say, right? So this thing is now called, this is known as capital S square. So capital S square is 1 upon n minus 1 sum of xi minus x bar whole square. So this is called corrected sample variance. Corrected sample variance, or the right sample variance which we use to estimate the sigma square. This is unbiased estimator. Is unbiased estimator. So students, in the exam, you may be asked, one thing that you may be asked is, uh, what is the relation between small s square and capital S square? Okay. So let me rewrite here. Relation between small s square and capital S square. In the MCQ, this question is asked. Okay. So what is small s square? Small s square is 1 upon n sum of xi minus x bar whole square. And what is capital S square? So that we have told just now, 1 upon n minus 1 sum of xi minus x bar whole square, I varying from 1 to n, I varying from 1 to. Now let us call this 1, let us call this 2. So if you divide equation number 1 and 2, so this same summation is same, so it will get cancelled out, and you will left with small s square divided by capital S, small s square divided by capital S square. This is equal to 1 by n divided by 1 upon n minus 1. Or you can say small s square upon capital S square is equal to n minus 1 divided by n. So this is the relationship between sample variance and corrected sample variance. Any doubt, students, in this? So 2-3 problems we have covered here. So problem number 1, if they ask you show that the sample variance is not unbiased, sample variance is biased. So that was the last question that we have done yesterday. Okay. And if they ask to show that the capital S square is unbiased, this new capital S square, so how you can do it? So one way is like you start from here, capital S square, and you solve all these terms. You find the expectation of capital S square, and then you show that this expectation is equal to sigma square. Okay. So other thing is like first you start with the small s square and then find out this relation, and in this relation you do the send this on other side, and then you call that cos this is equal to this one, that is why this capital S square is unbiased. So both the ways you can do this problem. Okay. So now we will move ahead. Okay, students, there are some problems, some exercise problems that you need to do. So let me give these things you as an exercise. So first exercise is this one. If we have not done this, okay, this is the first exercise. So you can note down. You should try this exercise. Second is second exercise is this one that I'm going to put here. So these two questions I'm leaving as an exercise. Okay. And now we will move to the next topic. So next is what is the meaning of consistent estimator? What is the meaning of consistent estimator? Okay. So the meaning of consistent estimator topic is consistent estimator. So the meaning of consistent estimator is that, like, if your sample size is increasing, then what should happen? Then the value of the estimator and the value of the parameter, they both should be same. They should be very near. Okay. It means when we are increasing the sample size, we are going near the population. Then whatever data or whatever the information we are getting from the sample, that should be correct regarding the population. So this is the general meaning. Now mathematically, how we can express this? So mathematically, we say an estimator, T Tn is said to be consistent estimator if this Tn converges to consistent estimator of whose estimator. So it is an consistent estimator of parameter theta if this Tn converts to theta in probability. So what is the meaning of convergent probability? It means like the chance or the probability that Tn is near this theta should approach to 1. Okay, it means the probability that uh, this the distance between Tn and minus distance between this Tn theta is uh, this is approaching to 0. This probability should be 1 as an approach to infinity. So this is a general meaning. Okay, so you don't need to remember all these things. Okay, the common meaning is like common sense meaning is that this Tn and the parameter, they should be same when sample size is large, when n is large. Okay, that means whatever you're trying to estimate is correct about the population. When you increase the sample size, chance of that should be near 100% chance should be here. Okay, so if you even if you don't understand this, that is fine, because we are not going to use this to solve the problems. So what we will use for solving the problem? Okay. For solving the problem, we will use these two things. So first thing is this, the conditions, These conditions I am going to put here. So we will use these conditions to check whether an estimator is sufficient estimator or not. Oh, sorry, consistent estimator or not. So conditions for consistency of an estimator. What are the conditions for the consistency of an estimator? So when we say an estimator is consistent estimator, means how we can check whether an estimator is consistent or not. These conditions are sufficient. These are not necessary conditions. Sufficient conditions means if these conditions are true, then 100% the estimator will be an consistent estimator. But if it is consistent estimator, then it is not necessary that this will be also true. Okay, there is one side, so leave it. But suppose you want to show that you are given an estimator and you have to show that it is a consistent estimator. So how you can show it? Uh, so first thing you will do is, so instead of this gamma theta, don't use this gamma theta, just use a theta. So first thing is the expectation of this Tn, it should approach to theta. Okay, means if you find the expected value of this estimator, then it should approach to theta when n approach to infinity, when sample size approach to infinity. And second is the variance of Tn should approach to 0 as n approach to infinity. I will give you example. Let me give you an example here. So what is an example of a consistent estimator? So the example of consistent estimator, this one. So prove that if you do sampling from normal population with mean mu and variance sigma square, the sample mean is consistent estimator of mu. So we have to show that sample mean is consistent estimator. So what is the meaning of sample mean? Sample mean means x bar. So we have to show that x bar is consistent estimator of this mu. Okay. So population means. So from the sample mean, we can estimate the population means. So we have to show it. So if you want to show that some estimator is consistent, so you can use these two conditions that we have just studied. First, we'll find expectation of that estimator, and that should be equal to the parameter. So first I will find the expectation of uh, this sample mean. So you know what is the expectation of sample mean? So that is always mu. Okay. So if you want to do it like same thing, I have to repeat again and again. If you want to do it, so what is the meaning of x bar? X bar is x1 plus 2 plus xn and divide by n. 1 by n is constant, 1 by n will come outside. So expectation of x1 plus expectation of x2 plus expectation of xn. Now because the sample has been taken from the normal population where mean of every member is mu. So it means expectation of x1 is mu, expectation of x2 is mu, and all have mean mu. So you will get 1 by n, mu plus mu plus mu, n times. When n cancel, so you will get uh, mu only. So n mu times n mu upon n is n cancel, so you will get mu. Okay. So therefore, the first condition is true, that expectation of the parameter is equal to expectation of the estimator is equal to parameter, right? So because expectation of x bar is equal to mu, so therefore x bar is satisfying the first condition. Now we'll find variance of this x bar. So it should approach to 0 as n approach to infinity. So now what is variance of x bar? So yesterday we have found the variance of x bar in the beginning. I have told you these two things we are going to use multiple times. First was E of x bar is equal to mu. Second was variance of x bar. So variance of x bar we have found in the beginning. So that was sigma square upon n, right? Now this will equal to 0 if n approach to infinity. Because the sigma square is finite and you are dividing by infinite, then it will become 0. Okay, it means the variance is going to 0 of x bar. The second condition is satisfied, that the variance of Tn going to 0 as n approach to infinity. Therefore, this is an consistent estimator. So any doubt, student, in this? If there is any doubt, you please ask. Because I feel these problems are easy once you understand what is the concept. Okay. Okay. Now, I will tell you one property of this consistency. Okay, so that is called invariance property of consistency. And what is the invariance property of consistency? So invariance property of consistency. Okay, students, in the book, in the SC Gupta books, they are using this gamma theta in place of theta. But I prefer the theta only. Okay. So in the exam in place of theta, if you get gamma theta, don't get worried about it. Okay. So if Tn is consistent estimator of some parameter theta, and this psi is a continuous function, okay, then psi of Tn is a consistent estimator of psi of this. Let me erase all this. Let me tell you in another way. So if Tn is consistent estimator of theta, means with the help of Tn we can measure the value of theta with the 100% probability when n approach to infinite. Okay, so if Tn is consistent and you have some function psi, and psi is continuous function, psi is continuous function. If psi is continuous function, then in this psi you can put this Tn both sides. So apply this psi on both sides. The psi of Tn will be consistent estimator of psi of theta. Okay, if Tn is consistent estimator of theta, then psi and psi is continuous, then psi of Tn will be consistent estimator of psi theta. So for example, now we have done this example that mean is consistent estimator of population mean, right? For example, we have just seen that sample mean x bar is consistent estimator of population mean. So we have seen that with the help of uh, this sample mean, we can estimate the population mean consistently. Okay, and this function, if I take this function f of t is equal to t square, being a polynomial, this is a continuous function. This is continuous. So if we have continuous function, then both side we can put the this we can apply this function f on both side. So if I apply this function f on both side, so it means f of x bar is consistent. It will be consistent for f of mu. Now what is f of x bar? So in place of t, put the x bar. So you will get x bar square is consistent for f of mu. What is f of mu? In place of t, put mu. So you will get mu square. That means like if you know that x bar is consistent for mu, so x square will be consistent for mu square. In the same way, I can show x cube will be consistent for x bar cube will be consistent for mu cube. So this is the invariance property. Okay, so this is the invariance property of consistent estimator. Okay, that if this is consistent and we have a continuous function and psi is a continuous function, then you can apply this function on both sides. It will still remain consistent. Okay, so let me see some other example now. Okay, so this is the next question. The question is if x1, x2, xn are random observations on a Bernoulli variate X. Okay, so these x1, x2. Okay, Roshan is saying not understand. Roshan, what you did not understand? 729 just now. Okay, which part? Which portion? So meaning of consistent estimator. First of all, meaning of consistent estimator. Px. This is x bar square. Okay, 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 okay. Okay, let me explain this. So I have given, so first this is clear that this mean is a consistent estimator of mu. This part is clear. You, you need to tell me wherever you have, okay, this is clear, right? So we know that x bar is consistent estimator because we have shown just before it. Okay, and now uh, f of t is equal to t square is a continuous function. It is a polynomial. F of t is equal to t square is a continuous function. Do you agree? Yes, right. Okay. Okay. So let me do it. So this point is clear that f of t is equal to t square is continuous because it is a polynomial and every polynomial is a continuous function. Okay. Now, uh, so this is a result that I have told you invariance property of consistent estimator that if we know that Tn is consistent estimator of theta and psi is continuous function, then we can apply this function on both sides of this first equation, you can say, right? So x bar was consistent estimator of mu and its f of t is equal to t square is a continuous function. So I can apply this f on both sides. So f of x bar is equal to f of mu. It will remain the consistent. This is the property that I have told you here. Invariance property. This is the invariance property. Invariance property. So I can apply f on both sides if f is continuous. So till here it is clear where I have marked the tick or there is doubt here. Okay. Now, what is f of x bar? If you put x bar here in place of t in this function, in place of t, if you put x bar, what you will get here in place of t, put the x bar. So what will be f of x bar? It will be equal to x bar square, na? F of u. What f of mu? Okay, f of mu. Now in place of t, put the mu. If we have a continuous function, we can apply that continuous function on both sides. F was continuous, so can apply this on both sides. So f of x bar will be consistent estimator of f of mu. Okay, because x bar was consistent estimator of mu and f is continuous, so f of x bar will be consistent estimator of mu. This is the property, invariance property. Now what is f of x bar? F of x bar, if you put here in place of t, if you put x bar, you will get x bar square. So f of x bar is x bar square. So in place of f of x, I'm writing f of x, this x bar square. And what is f of mu? So in place of t, put the mu, you will get mu square. What this function do basically? It do the square, na? T square. This function do the square of a number that you put in it. So if I'm putting x bar, it will do square of it. If I'm putting mu, it will do square of it. Is that clear, Roshan? Okay. Okay, so let us move to this next example. If x1, x2, xn are random observation of Bernoulli variate x, taking the value 1 with probability p and taking the value 0 with probability 1 minus p. So in the chapter 3 or in the unit 3, we have done the Bernoulli distribution. In the Bernoulli distribution, a random variable can take only two values, means we can take any continuous function. Yes, we can take any continuous function. Here I have given you an example by taking t square, simple example, that like you can take x cube, you can take t cube also, you can take t plus t square also, any continuous function we can take. Yes, absolutely we can take it. So, yes. Okay, now in the unit 3 we have discussed about the Bernoulli variate. Okay, so Bernoulli variate means here only two outcomes are possible. One is success, other is failure, and so x can take only two values. Either x denotes the number of success, either zero success or one success will be possible in the Bernoulli distribution. We try only one time, right? And the probability of probability of one success we take by p. Probability of zero success means failure. Probability of failure we denote by q, and q is actually 1 minus p. So this we know in the unit 3. So they are just repeating this thing, that this x1, x2, xn, these are the random observation of the Bernoulli variate. It means they will follow the Bernoulli distribution. Okay. And this is given that probability of 1 is p, probability of 1 is p, and probability of value 0 is 1 minus p. Now we have to show that this one which is given to us here, it is a consistent estimator of p into p minus 1 minus p. Okay, so we have to show that it is a consistent estimator of p into 1 minus p. Okay, students, so first what I will do, I will show that this sum of xi divided by n is a consistent estimator of p. Okay, so how I will show? So you know this property you will use, that I will show that expectation of this is equal to p and variance approach to 0. Okay. Now first I am going to show, first we will show that sum of xi, I varying from 1 to n, divided by n, this is consistent estimator of p. First I will show this. Okay. So first I will show that this is a consistent estimator of p. How we can show the consistent? First, for consistency, if we show these two conditions, that the expectation is equal to that parameter and variance is equal to 0, then we are done. Okay. So first I will find the expectation of this. So what is expectation of this? The sum of xi divided by n, I varying from 1 to n. So this is 1 by n is constant. Sum of I varying from 1 to n, expectation of xi. So students, what is expected value of xi? If xi is Bernoulli random variable, then what will be the expected value of xi? So let me recall how we find the expected value of x in the Bernoulli distribution or in any discrete distribution. So we do summation for all possible values of x. The possible values of x are 0 and 1 here. X into probability of x. So 0 into probability of 0 plus 1 into probability of 1. Now what is probability of 1? P. So expected value of x is p. Okay. So we have 1 by n sum of p values. So how many values are there? N times. So we'll get n into p. Okay. So n cancel. So we got p. So first thing I have shown that the expected value of this is equal to p. Okay. Second, I will show the variance of this summation xi divided by n. This is equal to 0 when n approaches to infinity. So what is variance of this? So variance of this, so first of all, 1 by n is constant. From the variance, the square of the constant comes out, and we have variance of x1 plus variance of x2 plus so on, variance of xn. Now, what is variance of xi? If x is Bernoulli, x follows the Bernoulli variate, x is Bernoulli variate, then what will be the variance of each of these? What is the variance in Bernoulli distribution? In the unit 3, we have done this variance in the variance of the Bernoulli distribution. So that was P into Q. P into Q. Okay, variance of the Bernoulli distribution is P into Q, or you can say P into 1 minus P. Okay. So you will get here 1 upon n square PQ plus PQ and so on. How many times PQ? So you will get n times PQ. So n times PQ, so 1 n will be cancelled out and you will get PQ divided by n. Now this will approach to 0 if n approach to infinite, because PQ is finite, n approaching to infinity, finite upon infinite is 0. Okay. So therefore variance is approaching to 0 and this expectation of this is equal to p. It means this xi upon sum of xi upon n is a consistent estimator of p. Okay. So therefore t is equal to sum of xi divided by n is consistent estimator of p. Okay, so we have shown that this t is consistent t is consistent estimator of p. So we have shown that t is consistent estimator of p. But in the question, what we have to show? In the question, we have to show that this t, this thing I am calling as t, t into 1 minus t is consistent estimator of p into 1 minus p. This we have to show, right? Now, so how you can do it? So if I take this function f of t is equal to t into 1 minus t. So it is a continuous function. Is it continuous? Because it is a polynomial. T minus t square is a polynomial. Continuous. Why continuous? Because it is a polynomial. Being polynomial. Now apply the property of invariancy. So if you have something, you know that this t is consistent for p, and you know f is continuous. So in place of this t, you can put these things, right? So it means f of capital T will be consistent estimator of will be consistent estimator of f of t. So what is f of t? So here you put t into 1 minus t is consistent estimator of. So what is f of p? Put in place of t, you put p. So p into 1 minus. This is what we have to show. So what is t here? T is basically sum of xi upon n. So if you put here, we will get sum of xi upon n. 1 minus sum of xi upon n is consistent estimator of p into 1 minus p. Any doubt, students, in this? Is this clear? There is one more way to do this question also. Okay. So method number 2. Method 2. We have to make function according to question. Yes. We have to make, yes, we have to make the function according to question. The function should be continuous. Now next method 2 I am telling you to solve this question. Students, whenever we have Bernoulli random variable and we add the Bernoulli random variable finite number of times, like you are doing a trial n times. X1 means you are doing trial one time, but now you are doing trial n times. And if we add this x n times, then this x will follow binomial distribution. Binomial distribution. So in the binomial n and p is probability of success, np and x. Okay. So if x1, x2 are, these are Bernoulli distribution, and we add them, then it becomes binomial distribution. Okay. Because xi is basically xi is number of success in one trial, either 0 success or 1 success. If you are adding all successes, you will get total number of success when you try something n number of times. Okay. Okay. So the sum of xi, it follows the binomial distribution with parameter n and p. Okay. So if it follows by a binomial distribution and you take the if you take the this expectation on both sides, so what you will get? So what we will get? So we will get expectation of this sum of xi. So that I am calling capital X. So instead of capital X, let us call it as T, because capital X they are using for the Bernoulli distribution. So I'm calling this T. Now I have to show what we have to show. We have to show that this T upon n into 1 minus T upon n. This is consistent estimator of P into 1 minus T. Okay, so we have to show this. Or you can say we have to show T by n minus T square by n square is consistent estimator of P minus P square. Okay. So how we can do it? So we can try it like we will show that the expected value is equal to expected value is equal to this p into p minus p square, p into if I find the expected value of this first, t by n minus t square by n square. So this is 1 by n is constant, expected value of t minus 1 by n square is constant, expected value of t square. Okay. Now because t follows the binomial distribution, so expected value of t will be np divided by n minus 1 by n square as it is. What is expected value of t square? So for that we need to see that note that, let us call this as 1, variance of t. What is variance of t? You know that variance of t in the t is binomial random variable now, and what is variance of binomial random variable? That is npq. Mean is np and variance is npq. So mean was np. That is why I have written here in place of p of t. I have written np. So now what you do? So what is meaning of variance? E of t square minus e of t whole square. This is equal to npq. Now e of t square is equal to npq plus e of t whole square. So npq as it is. What is expectation of t? What is the mean of binomial random variable? That is np. So you have np square here. Now put this in equation number 1. Use this 2 in equation number 1. So use in 1. So you will get expected value of t by n minus t square by n square. This is equal to np divided by n. So n cancel, minus 1 by n square as it is, npq plus n square t square. So if you simplify this, what we are getting? So we are getting p minus pq divided by n minus p square. Right, we are getting this thing till now. Let me simplify this. So p minus p into 1 minus p divided by n minus p square. I think we are getting some extra term. I am doing it correctly, right? We are doing it correctly. So if I have missed some detail or something here, do tell me. Like is expectation okay? Oh, fine. So if n will approach to infinity, this pq by n will approach to 0, na? So this is equal to p minus p square if n approach to infinity. So when n approaching to infinity, then the expected value of this t by n minus t square by n square, this is coming out to p minus p square. So first we have to show this now. So first thing done. So we have shown that expected value of this is equal to p minus p square. Okay. Second, you will show that variance of this. Second part, you will show the variance of this t by n minus t square by n square. This is going to 0 as n approaching to infinity. So first apply the properties of variance. So variance of t 1 by n square, variance of t plus 1 by n power 4 variance of t square. Okay. Now, what is variance of t? T is binomial random variable, so its variance is npq divided by n square plus what is variance of t square? Variance of t square. Hmm. Variance of t square we need to know. Okay, so I will see this point. I think I'm not clear about this, how to find the variance of t square. This point is not clear to me. Okay, so first part will approach to 0 because we have in the division you have n and pq is constant. So n as n approach to infinity, this will approach to 0. But how to find variance of t square, I have no idea. So right now, so I will leave this point for the time being. Okay. So till then, we can move to next example. The next question is an easy, and this is asked multiple times in the exam. So you can see this. What is the problem? So this is the question. Okay. So a random sample, x1, x2, x3 of size 3 is drawn from students. Do see this question carefully because as I've told in Unit 5, there are uh, finite, there are very few problems which are repeatedly asked. Okay, so that is why focus on this problem because this is one of such problems. Okay, so in a random sample x1, x2, x3 of size 3 is drawn from the normal population with unknown mean mu and variance sigma square. Okay, so now we have this population and mean of this population is mu and variance of the population is sigma square. So from this population we have taken the sample of 3 x1, x2 and x3. Okay, uh, T1, T2, T3 are the estimators used to estimate mean value. Okay, so we have three estimators T1, T2 and T3 and these are used to estimate what? Mean. Mean means mu of the population. Where T1 is, so you are given T1, x1 plus x2 minus x3. You are given T2 which is 2x1 plus 3x3 minus 4x2 and you are given T3. T3 is 1 by 3 lambda x1 plus x2 plus x3. So first they are asking are T1 comma T2 are unbiased estimators. So are these unbiased estimator of mean? So because these are used to estimate the mean, right? So we have to check are these unbiased estimator of mu. So for that we have to check is the expected value of T1 is equal to mu or is the expected value of T2 is equal to mu. If it is true, then they are unbiased estimator of mu. So let me, you know now what is the meaning of unbiased? Unbiased means expected value should be equal to the parameter. Then they are unbiased. So first I will find expected value of T1. So what is expected value of T1? So what is T1? x1 plus x2 minus x3. x1 plus x2 minus x3. So which is equal to expected value of x1 plus expected value of x2 minus expected value of x3. Now what is expected value of x1 students? The sample has been taken from the population where mean of this population is mu. It means if I take any sample x1, x2, x3, those will also have mean mu. So mean of x1 is mu, mean of x2 is mu, and mean of x3 is also mu. So 1 mu and mu will be cancelled, so we got mu. So it means the expectation of T1 is same as mu, so therefore T1 is unbiased estimator of mu. So is there any doubt in this question? So this is easy. I hope all will understand this part. Now we will show that expected value of T2. What is it? Let us find the expected value of T2. So why we are finding expected value of T2? Because in the first part they asked to check us whether these are unbiased or not, unbiased estimator of mean or not. If they are unbiased estimator, then their expected value should be equal to mean. Okay. Why mean we are checking here? Because they are used to estimate mean. Okay. So now I will put 2x1 plus 3x3 minus 4x2. So expected value of 2x1 plus 3x3 minus 4x2, right? So now I will use the properties of expectation. Constant will come out of the expectation. Again, same logic, because the sample has been taken from the normal population with mean mu. So all these three have mean mu. So you will get 2 times mean minus 3 times plus 3 times mean minus 4 times mean. 3 into 5, 5 minus 4, 1. So you get 1 time mean mu. So it means therefore expected value of T2 is also mean. So it means T2 is also unbiased. So T1 is unbiased, T2 is unbiased. Okay. Now students, I will suggest you to do the B part and tell me the answer of B part. I will give you this an exercise, so tell me the answer. So yes, students, anybody done? Okay, so 2 students have answered. Yes, your answer seems to be correct. Okay, so now let us see how to do it. Okay, so they are asking for which value of lambda T3 will be unbiased. So T3 will be unbiased means the expected value of T3 should be equal to the mean, because these are used to estimate the mean. These are the estimators of means, right? So we will find the expected value of this T3. So B part I am doing. B part expected value of T3, and we will show it will be equal to mu, because you are told that this T3 is unbiased and we have to find lambda. For what value of lambda it will be unbiased. So if it is unbiased, then its expectation should be equal to mu. Now what is T3? T3 is 1 by 3 lambda time x1 plus x2 plus x3. So this is equal to mean mu. 1 by 3 is constant. Lambda is also constant. So expected value of 1 plus expected value of x2 plus expected value of x3. This is equal to mu. Now 1 by 3 as it is, lambda as it is. What is expected value of x1? Because these are the samples taken from the population where mean is mu. So everybody will have mean mu. Mu is equal to mu. So now you will send this 3 mu on other side. You will get lambda mu plus 2 mu equal to 3 mu. So now this lambda mu is equal to 3 mu minus 2 mu. So lambda mu is equal to mu. Mu cancel out. So we'll get lambda is equal to 1. So if T3 is unbiased, then lambda should be 1. Yes, correct. Okay, so this is the correct answer. Now we will move to third part. With this value of lambda, is T3 a consistent estimator? So like we have checked that what is the value of lambda? 1. So now we'll put 1 here. If you put 1 here, then is it consistent or not? So C part is easy. So if you put lambda is equal to 1, so the T3 will become x1 plus x2 plus x3. They are asking, is it consistent estimator? So if you see T3 carefully, what is it actually? It is sum of the values divided by total number of values, right? So it is mean of x1, x2, and x3, mean of a sample, and mean of the sample is consistent estimator. We have done the proof of it. That mean is always consistent. Okay. So as T3 is sample mean, so you can write in this way how you will answer this question. So you will say as T3 is sample mean and sample mean is consistent estimator of population mean. Therefore, T3 is consistent. This answer you have to give. Okay. Now I will move to the next example. Okay, so next we will move to the next topic. That is what is the meaning of efficient estimator. Okay. So now the two things are remaining from the unit number 5. One is the meaning of efficient estimator, and second is the maximum likelihood estimator. Okay, so both topics, these two topics are there, which are pending from unit 5. So you can see there are very less number of problems in unit 5. So if you prepare them well, if you practice these problems, whatever problems I am doing here, whatever exercise problems I have given to you, so you can do very well. Okay, so do try these and do practice unit 5. Don't think that you have to leave the unit 5. Don't make this mind. Okay. So also like there are very less number of MCQ questions from unit 5. Okay, because there are only a fixed number of topics, no much variation is there. So MCQ question, if you prepare the 15 to 20 MCQ questions regarding these basic definitions, then it will be very good. Your exam will go very good in MCQ also from this unit. Okay, so first is if of the two consistent estimator T1 and T2 of a certain parameter theta, if the variance of T1 is less than variance of T2, so both T1 and T2 are consistent, but the variance of T1 is less than variance of T2 for all sample sizes, okay, whatever sample size we take, then we will say that T1 is more efficient than T2. If there is less variance in the estimator, it means it is more efficient. Okay, less the variance, more the efficient. Okay, but both. Uh, so this comparison we do only in the consistent estimator. If they are not consistent estimator, then there is no meaning of comparing the variance. Okay. So if variance of T1 is less than variance of T2, then we will say T1 is more efficient. T1 is more efficient as compared to T2. Less variance, more efficient. Okay, less is the variance, more is the efficiency. Now, what is the meaning of most efficient estimator? This is the meaning of efficiency. First, I have told you, like when we say an efficient, one estimator is more efficient than other, if the variance of that one is less than variance of other one. Second is, what is the meaning of most efficient estimator? Most efficient estimator of parameter theta. So when you so if we have so many estimators which are consistent estimators for this parameter theta, and out of those consistent estimator, the one which have smallest variance, the one which have smallest variance is called the most efficient estimator. Okay. So in this world, we can write in this way that in a class of consistent estimators of a parameter, there exists one whose sampling variance is less than that of any of such estimator. It is called the most efficient estimator. The one whose variance is smallest, you can say, that is the most efficient. Okay. This comparison we do only in the consistent estimators. First thing is we need the consistency. Only then we see the efficiency. If the estimator is not consistent, we will not see the efficiency. And out of the consistent estimator, which the one which is the most efficient, uh, that we call as most efficient estimator. Okay. Now next thing is what is how we determine the efficiency of an uh, efficiency of an estimator. So efficiency, next definition is efficiency. How we determine the efficiency. So if T1 is the most efficient estimator, first of all we see which one is the most efficient. So let us say T1 is the most efficient. Okay, T1 is the most efficient and it has the variance V1, and T2 is some other estimator and the variance of T2 is V2. And if I want to find the efficiency of this T2, so what I will do, I will divide the variance of this T2 with the most variance of most efficient estimator. So reverse we have to do. The variance of most efficient we have to divide with the variance of this T2. You know the variance of most efficient is the smallest one. Variance, the one which is most efficient, that has smallest variance. It means V1 is always less than V2. So therefore the efficiency is always less than 1. And it is greater than 0 because variances are always greater than 0. Variance cannot be negative, right? So it is square of the deviations, average of the square of deviations. That is why it cannot be negative. So efficiency is always between 0 and 1. So efficiency is always between 0 and 1. Okay. So this is the definition of efficiency. Now there are not much problems from this efficiency. efficient estimator. Whatever problems I have, let me put these problems. So this is the first problem. So x1, x2, x3, x4, x5. Uh, a sample of size 5 is drawn from the normal population. The sample has been drawn from the normal population with unknown mean mu. So mean of the population is mu. And consider the following estimators to estimate mu. So what we want to estimate mu with the help of these estimators T1, T2, T3. Okay. So where lambda is such that T3 is unbiased estimator of mu. So lambda 3 is in such way that this T3 is unbiased. So what is the meaning of unbiased? We will apply expectation on both sides. We will keep it equal to mu and then we'll find the value of lambda. Okay. So first we have to find the lambda. Second, are T1 and T2 unbiased? So is T1 unbiased, students? So you know it is a sample mean. Sample mean is unbiased estimator. Otherwise you can take the expectation of this and you can show the expectation is equal to mu. Okay. In the same way we can do this T2. We'll take the expectation of T2 and we will show it is also equal to is it really equal to mu or not? So mu plus mu, 2 mu. No, it is not equal to mu. It is equal to 2 mu. Okay. So I am talking about this. If I find the expected value of T2, so that is expected value of x1 plus x2 divided by 2 plus x3. Apply the properties of expectation. 1 by 2 is constant. Expected value of x1 plus expected value of x2. This 1 by 2 is in the division of both and expected value of x3. Now because the sample has been taken from the normal population, this population is normal population where mean of every member is mu. So mean of x1, x2, x3, x4, x5 all will have mean mu. So 1 by 2 mu plus mu plus mu. So 2 mu by 2 is mu, mu plus mu is 2 mu. So expected value of T2 is 2 mu, which is not equal to mu. Okay, it means T2 is not unbiased, T2 is biased. Okay. And what other thing we have to see? State giving the reason, the estimator which is best among T1, T2 and T3. So student, first of all tell me the value of lambda. But in the T3 what is lambda? What is lambda in T3? So any student have an answer? Roshan said 0. Other student also please answer these questions. Okay, these are not difficult questions. So we'll take the expectation of T3 and that will be 2 times mu plus 3 mu and plus lambda mu is equal to mu. So 3 mu cancel out. So yes, you will get lambda is equal to 0. Lambda is equal to 0, right? Okay. So lambda is equal to 0. So now we have this T1, T2 and T3 and we have to tell which one is best among these T1, T2 and T3. So what we will do, best means the most efficient we will find. So we'll find variance of each of them and then we will see whose variance is maximum, whose variance is minimum. Okay. So first I am finding the variance of T1. Variance of T1. What is variance of T1? So that is variance of, what is T1? X1 plus X2 plus X5. Sorry, X5 divided by 5. So 1 by 5 is constant. But if you take a constant out of variance, the constant does not comes out. The square of the constant comes out. Variance of x1 plus x2 plus x5. Okay, so this property I have used. So variance of ax is equal to a square into variance of x. T1 and T2 check unbiasedness. Roshan, I have not doing that unbiasedness check, na. In the, as I have told you, for the T2 we have checked that T2 is not unbiased, right? So we have checked here that expected value of T2 is not equal to mu, and T1 is actually a sample mean. Sample mean is always unbiased. Okay, so that is why I have not done that T1 is unbiased. Okay. So now we are finding the variance so that we can tell which one is best estimated among these. So variance of this, now I will apply the 1 upon 25. So variance of x1 plus variance of x2 plus variance of x5. So because all these are from the normal population, all will have same variance, sigma square, sigma square, sigma square. So 5 times I will have sigma square. So 1 by 5 sigma square I will get. Okay. In the same way, I will find variance of T2. If I find variance of T2, so this variance of T2 will be variance of x1 plus x2 divided by 2 plus variance of x3. So 1 by 2 is constant. If we take it out, 1 by 4 will come out actually using property of variance. So variance of x1 plus variance of x2 plus variance of x3. Now because they have been taken from the normal population, everyone have variance sigma square plus sigma square. So 1 by 4, 2 times, so 2 times sigma square plus sigma square. So we got 3 by 2 sigma square. T2 is biased, so no need to check, na sir. Uh, Here, in terms of best estimator, they just ask the, I think they just ask the efficiency. They are not talking about the biasness or unbiasedness. So I am checking the efficiency. Okay. And the third one is variance of T3. So T3 variance. So directly I'm doing in the mind. Okay, you can do also 1 by 3 first will come as 1 by 9, and 2 square is 4, 4 and 1 square 1. So 4 and 5, 5 by 9 sigma square. If you find the variance of T3, it will be 5 by 9 sigma square. So now you need to compare out of these three which one is smallest. Is 1 by 5 is smallest, or is 3 by 2 is smallest, or 5 by 9 is smallest. So which one is smallest? The smallest one is this one, 1 by 5. 1 by 5 is smallest, so T1 is most efficient estimator. By the way, T1 is consistent also because it is sample mean. Sample mean is always consistent. Okay. So one more practice question I will put here. I will not solve this practice question. This is an exercise for you students. So this is the problem that you need to solve. So you can note down this problem and we will move to the last topic of this unit 5. Okay, so sufficient estimator is not in your syllabus now. This is a good thing. Uh, Earlier, you have to see the 4 properties. You have to study that unbiasedness, consistency, efficiency, as well as sufficiency also. But now sufficiency has been removed from the syllabus. Okay, so that is why we will just now go to the last topic, which is maximum uh, likelihood function, maximum likelihood estimator, MLE. Okay, so this is an exercise for you guys. This question. This is same question, I think. Okay, there is one more part here. Which one is best estimator? First 3 parts are done, and you're asked the fourth extra part. The new part here is which one is best among these. So you will find out that the variance of these estimators, and then you will which one is best. Okay. So next topic is maximum likelihood likelihood estimator. Maximum likelihood estimator. Okay. So what is the meaning of maximum likelihood estimator? Before that, we need to understand what is the meaning of likelihood function. Okay. What is the meaning of likelihood function? So the meaning of likelihood function. So let x1, x2, xn be a random sample of size n from a population with density function f of x comma theta. So students, what is this theta here? Okay, what this theta denote? What this theta denotes? Okay, theta denote the parameter basically. Like in case of normal distribution, what are the parameters? In case of normal distribution, the parameters are mean and standard deviation. If you know the mean, if you know the standard deviation, you can find out all the things, right? In case of binomial distribution, the parameters are n and p. N is total number of trial, p is probability of success. In case of negative binomial distribution, the parameters are k and p. So k is excess number of trials required to get k success, right? In different distributions, we have some parameters. Okay, so like in normal distribution, this mu and sigma was parameter. In the Poisson distribution, the parameter was lambda, right? Average number of events, right? That lambda was the parameter. So in every distribution, we have some parameter. Okay, so that we are denoting by theta. Okay, it depends on distribution to distribution about which distribution we are talking. And if the density function is f of x comma theta, the density function is f of x comma theta, then the likelihood function of the sample values x1, x2, xn is usually denoted by L of theta. So likelihood function we denote by L theta. And what is it basically? It is product of the probability density functions. Okay, it is product of their probability density functions. Okay, so for example, if in the Poisson distribution, so you have you have taken some sample x1, x2, x3, and x5, and you want to know what is the likelihood function of this in the Poisson distribution. So what you will do, sir, please explain one more statement of likelihood connection problem there. Okay, so I am repeating. What is the meaning of likelihood, maximum likelihood estimator? Okay. So students, first I told you, like in every distribution, like whether it is normal distribution, whether it is a Poisson distribution, whether it is gamma distribution, there are some parameters. No? In the normal distribution, the parameters are mean and standard deviation. In the binomial distribution, the parameters are number of trials and probability of success. In the negative binomial distribution, the parameters are k and p. In the Poisson distribution, the parameters are only one parameter is there, lambda. Okay, so these are the parameters, like, and if I take some sample, let us say x1, x2, x5, I have taken the sample from the Poisson distribution. From the Poisson population, I have taken the sample. Now, what is the meaning of likelihood function of the sample? So likelihood function will be, so in place of this x, we will put the sample values. The probability of x1 comma lambda into probability of x2 comma lambda into so on probability of x5 comma lambda. So this will be the likelihood function of sample of 5 things. So likelihood function just means that you are multiplying the probability density functions at the values of the sample. Okay. So this symbol, students, this symbol here means this pi kind of symbol, this big pi kind of symbol means product. So this is product of f of x1 comma theta into f of x2 comma theta and so on, product of f of xn comma theta. Okay, product of n functions. If we are taking sample of n values x1, x2, xn, so in the density function we'll put x1, x2, xn and we'll multiply. I will give you an example. Don't worry, students. Let me give an example of. So suppose we have taken a sample from Poisson distribution. So first of all, in the Poisson distribution, what is the probability function? Poisson distribution, in the Poisson distribution. So in the Poisson distribution, if you want to find the probability is lambda power x and e power minus lambda divided by x factorial, right? So this was the formula. So you have t also here, but for the time being, let us take t is equal to 1. In 95 of the percent of the problems, we solve with t is equal to 1. Okay. So in this, now if I have taken the sample x1, x2, and xn, okay. So what will be likelihood function of that? So first I will put these values here x1, x2, xn, and then I will multiply them. Okay. So likelihood function of this parameter lambda will be probability function at x1 comma lambda into probability function at x2 comma lambda, and so on in the end the value at xn comma lambda. So now put these in this here. So in place of x, now first put x1. So lambda power x1 into e power minus lambda divided by x1 factorial into lambda power x2 e power minus lambda divided by x2 factorial, and so on lambda power xn e power minus lambda divided by xn factorial. So what we are doing basically in the probability function, we are putting the sample values and then we are multiplying as many as sample values are there, and that we are calling the likelihood function. So this is the likelihood function of lambda. Okay, so this is the likelihood function. Likelihood function. Same we can do for the normal distribution. Same we can do for the binomial distribution. Any doubt? Is this clear? अक्षय अक्षय तो स्टार्टिंग में तो जवाब देता था, बट बीच में बिल्कुल ही अलग हो गया है. नो रिप्लाई, नो क्वेश्चन, नो क्वेरी, एंड अंकित now only in chat. Rarely any. Today he is silent. Most of the students are today silent. Students, this maximum likelihood estimator is an important topic, and there is a fixed method to find the maximum likelihood estimator also. Okay, so please don't lose focus. Okay. So what is the meaning of maximum likelihood function? We multiply the probabilities, this density function or probability distribution function for the different values of samples. We multiply them together, and that we call likelihood function. Now, as clear from the name, we want to find the maximum likelihood estimator. So maximum likelihood estimator is that value of the parameter for which this likelihood function is maximum. Okay. So what is the meaning of maximum likelihood estimator? It is that value of the parameter theta MLE, maximum likelihood estimator, uh, is that value at which L of theta is maximum, at which likelihood function is maximum. So first we will find the likelihood function, and then we will find the maximum, the point where this likelihood function is maximum, and that parameter will call that estimator will call maximum likelihood estimator. Okay, so let us do an example so that it is more clear to you guys. So first example. So first, now how we will find the maximum likelihood estimator? So steps to find maximum likelihood estimator. This is asked. Okay, steps to find maximum likelihood estimator. So there will be three steps. First, we will find likelihood function L of theta. First, we will find likelihood function. Then step 2, we'll take log of, we'll find log of L theta. So students, why we are finding log of L theta here? What is role of this log L theta? So basically we want to find the maximum value of L theta. Okay, but L theta is so complicated, like there are so many terms in the product. You can see here, there are lots of terms which are in product. So finding the maximum value is difficult. But once we take the log and then we apply the property of log, you know that this log of A into B, this is log A plus log B. So many things will become simples using these properties. Log of m power n, log of m power n. This is n times log m. Okay, so these things you have to remember, these log formulas which will be useful. And third step is how we find the maximum value of any function. So we will take the derivative of this with respect to the parameter, and we will keep this derivative equal to 0. So these are the three steps to find the maximum likelihood estimate. Where is the maximum value? Their derivative is 0, right? So this thing we are using. So first we find the function, then we find the log of the function, then we do derivative of log of function, keep it equal to 0. So wherever the log will be maximum, at the same point, the function will also maximum. And yes, any doubt? Product convert into addition with the help of log. Yes, right. This is valid. So this is the reason why we are converting, why we are taking log, so that we can convert the product into summation. Okay. So let us do an example. Examples will make the concept clear. Okay, so these are the three steps to find the maximum likelihood estimator. So first example, multiple time exam question. Okay, so first I should do the Poisson distribution question. Find the maximum likelihood estimator. So question is, find the maximum likelihood estimate for the parameter lambda of Poisson distribution on the basis of a sample size n. Okay, so let us see how we will tackle this problem. See the question. So solution. Students, first of all, we will write the probability density function of the distribution which they are talking about. So because they are talking about the Poisson distribution, so that is why I am writing the probability density function of a probability distribution function of Poisson distribution. So that is lambda power x e power minus lambda divided by x factorial. This distribution function we have to remember in the unit 3, unit 4. There are 4-5 kind of distributions which we have to remember. Now, what is the meaning? So they have they have taken a sample size of n. So let x1, x2, and xn be a random sample. Okay. So let x1, x2, xn be a random sample. Okay. So first we'll find the likelihood function. Step 1. First we'll find likelihood function L of theta. So step 1, find L theta, but in place of theta, now we have the parameter lambda. So L of lambda we will find. Now parameter is lambda. So L of lambda is in the probability distribution function. In place of x, we'll put first we'll put x1, then we'll put x2, and so on, and then we'll put xn, and then we'll multiply. So put here in this. Let us call this as equation number 1. If I put x1 there, so you will get lambda power x1 e power minus lambda divided by x1 factorial into lambda power x2 e power minus lambda divided by x2 factorial into so on. In the end, we have lambda power xn e power minus lambda divided by xn factorial. Okay, so e power lambda, e power lambda, e power lambda. So it is how many times? N times. So you have e power lambda, e power lambda. So this term is n times getting multiplied. So you can write this as e power minus n lambda. Okay, because e power minus lambda, e power minus lambda, if you multiply, powers get added, right? Students, if you multiply e power minus lambda with e power minus lambda into e power minus lambda, if there are 3 times, then you will get e power minus lambda, minus lambda, minus lambda, that is e power minus 3 lambda. Power will get added now. Base same power added. So minus lambda plus sorry, because they are in the negative. So minus lambda, minus lambda, minus lambda, which is e power minus 3 lambda. So here they are n times. So e power minus n lambda we will get, right? Now lambda power x1, lambda power x2, lambda power xn, base same, lambda power will get added. So lambda power x1 plus x2 plus up to xn. This is a very important question which I am doing right now. x1 factorial multiplied with x2 factorial, and in that multiply xn factorial. So you can check the PYQs. So there you will find this problem. Okay. So this we have found the L lambda, or you can say we have found the maximum likelihood function of lambda. So we have found the maximum likelihood function. Now what is step 2? Step 2 is we will take log both sides. So you can see here, these are the steps. First we find the L theta. Now we will take the log both sides, and after that we will do derivative with respect to parameter. So log of L, this is equal to log of e power minus n lambda into lambda power x1. So we can write this sum as, summation. So we can write this as sum of xi's I varying from 1 to n divided by this product of xi's. So x1 factorial up to xn factorial. So any doubt, students, in this? Okay. So this will be, now I will apply the properties of log. So what is the first property that I am going to apply? The first property I will apply is log m upon n. If two numbers are in division, then log of them is log m minus log. So this is one property. Second, I will apply log of m into n. That is log m plus log n. So these two properties I will currently apply, and after that I will also apply log e 1. Log e is 1. and more log m power n. This is equal to n log m. So we will get log of e power minus n lambda plus log of lambda power sum of xi's minus log of product of, so product we can write using this symbol, pi symbol, I varying from 1 to n, product of xi's factorial. Any doubt in this, student? So this is, you can like log m upon n, log m minus log n, then log m into n, log m plus log n. Now log m power n. So this power will come in the front, minus n lambda in the front. Log e is 1. For the timing, let me write log e here. Plus this power will come in the front, summation xi I varying from 1 to n, log of lambda minus log of product of I varying from 1 to n, xi factorial. So this is log L. So we have one more simplification we do. Log L is equal to minus n lambda, because log is 1, plus sum of xi into log lambda. Now this we don't need to solve this last one, log of this product. Why we don't need to solve this product in the end? Because in the next step we have to do the derivative with respect to lambda. And because this term does not contain the lambda, so derivative of this will be 0. Okay, step 3. What was step 3? We will do, to find the maximum value, we will do derivative of this with respect to lambda and keep derivative of this log L, and we will keep this derivative equal to 0. So you can see this is the third step. Do the derivative with respect to parameter and keep it equal to 0. This third step. Okay. To find the maximum value, we are doing the derivative with respect to lambda and keeping it equal to 0. So let us do derivative here. N is constant, minus n is constant, derivative of lambda with respect to lambda 1. So we get minus n plus, now this sum of xi does not contains lambda. Derivative of lambda is 1 by lambda. So we will get sum of xi divided by lambda, because derivative of log lambda is 1 by lambda, and this term do not contains any lambda, so derivative of this is 0. So minus 0 equal to 0. So from here we will find the value of lambda. So lambda is the sum of xi upon lambda is equal to n, or you can say lambda is equal to sum of xi divided by n. So if we take this lambda as sum of xi upon n, so this will be the maximum likelihood estimator for the lambda. So MLE, maximum likelihood estimator of lambda, MLE. Yes, so any doubts, students? So you can see that the maximum likelihood estimator of Poisson distribution is basically sum of the values divided by total number of values, right? So which is mean, and the lambda also denote the mean. Okay, so it means sample mean is the maximum likelihood estimator of this Poisson distribution. Okay. What is benefit of maximum likelihood estimators? So why we find the maximum likelihood estimators? Okay, because these are always consistent. Okay, there are some properties. These are always these are consistent. These are unbiased. Let me check whether it are unbiased or not. So MLE is also most efficient estimator. Okay, maximum likelihood estimator. These are the properties I will. So let us. Why not write the properties of this maximum likelihood estimator? So next topic is properties of maximum likelihood estimator. The topic is properties of maximum likelihood estimator. So we will do more question on this maximum likelihood estimator. Okay. So properties of students, like we have found the value of this lambda. So this value of lambda in terms of sample things. Okay. So these xi are sample. They belong to sample. But lambda belongs to population. Okay, so in place of lambda, we can use the lambda cap to denote that this is a estimator of lambda. So no problem, you can use lambda also. So you why to confuse you guys? Okay. So what are the properties of maximum likelihood estimator? The first property is maximum likelihood estimator are always consistent estimators, but they need not to be unbiased. Okay. So maximum likelihood estimators. So first property is maximum likelihood estimators are always consistent, but they need not to be unbiased. They can be biased. For example, the maximum likelihood estimator of the mean is sample mean that we will show in the normal distribution. Okay, in the normal distribution, we will prove it that the maximum likelihood estimator of mean is sample mean, and maximum likelihood estimator of these variance is small s square, that is sample variance. Okay. Uh, so mean is unbiased and consistent, no problem. But this small s square, you have known in the when we have done the consistent estimate, we have shown we have shown that it is unbiased. Okay, we have shown it is unbiased estimator of not unbiased. It is biased estimator of sigma square. Capital S square was when we have to make the correction in the beginning of the first thing today we have discussed was this one, that this small s square is biased. Okay, so that is why we take the capital S square, corrected sample variance. Okay, so here they are saying that small s square is consistent and it is not unbiased, but it is the maximum likelihood estimator of s square. It means maximum likelihood estimator need not to be unbiased, it may be biased also, but it is always consistent. It is always consistent. Now second property is, there may be question in the exam from this MCQ question from these properties. Second property is, this was property number one. Property number two is MLE if exist, it is the most efficient estimator in the class of such estimators. It is most efficient. Okay, so you don't need to check the efficiency, because you know if it is MLE, it means it will be definitely most efficient estimator. For example, in the Poisson distribution, the MLE or maximum likelihood estimator of lambda was sample mean and sample mean. So we can say sample mean will be the most efficient for the Poisson distribution. Okay, so this is the second property. Is there any doubt? What a amazing life for kids. There are planning, no tension, no DSA, no grade upgradation, tension, no drive tension. Okay, that is true. So as a kids, we don't have any kind of tension. We are free from all these worries, and I hope always this should be true.